All right, we are recording, and I'll turn it over to you, Natalie, for the introduction.
All right, thank you. So it's my pleasure to introduce my colleague and friend, Dr. Daniela Jones. Dr. Jones is an assistant research professor in the Biological and Agricultural Engineering Department here at NC State, and she also has a joint faculty appointment with Idaho National Lab. She's the developer and director of the new Agricultural Data Science Graduate Certificate here at NC State. And she's also graduate faculty in the Operations Research Program, a faculty fellow in the Center for Geospatial Analytics, and a faculty affiliate of the Ag Biofuse program. She develops data-intensive algorithms and applies diverse modeling and optimization tools to solve large-scale problems that arise in the areas of transportation, logistics, and renewable energy systems. And she earned her PhD in bio and ag engineering from Texas A&M, where she was also an Alfred P. Sloan Scholar. And she received her master's and bachelor's of science degrees in industrial engineering with an emphasis in operations research from Mississippi State University. And before landing at NC State, she was a postdoctoral research associate at Duke University, where she performed quantitative and qualitative research on student interventions and supported programming to bring more students from underrepresented undergraduate and to bring more students from underrepresented backgrounds into the biosciences. So with that, I'll go ahead and pass it off to Dr. Jones. Really looking forward to your presentation.
Thank you. All right, I'm going to share my screen. And present. There you go. Thank you for such a kind introduction, Dr. Nelson. And thanks to all in advance for your attention as I discuss strategies to mobilize carbon resources from agriculture for conversion to bioenergy while applying precision agriculture to mitigate climate change. I understand that the audience today is very diverse in discipline and research applications. So I wanted to start with my presentation by taking a bird's eye view of energy in the US to explain where my research lies. This graph shows the total energy consumption in the US each year. In total, the US consumes just under 100 watts of energy. Now I want us to focus on where is most of our energy being used. This graph is similar to the previous one, except for that the consumption is divided in sectors. As you can see, the industrial and transportation sectors together use 55 watts, or about 60% of the total national energy consumption last year. My research mainly lies into displacing the energy sources for transportation, but truly we have the potential to displace the energy sources of all the subsectors. This Sankey diagram has energy sources on the left and consumption sectors on the right. My goal is to translate my research so that biomass has a bigger size of the pie in terms of energy sources and displaces non-renewables such as petroleum, coal, and non-biogenic natural gas. My career has focused on the renewable source that lets us have energy in the form of liquid, which is biomass or agricultural products. Before I continue, I do want to acknowledge that given the current administration efforts to electrify cars, there's the possibility that we will not need liquid fuels for terrestrial transportation. But we could also have a future of hybrid cars, and most likely we will still need jet fueled in the liquid form. The major barriers to bioenergy production are feedstock cost, reliable supply, and uncertainty. This uncertainty is mainly due to extreme weather events and their impacts on yield. One way to overcome feedstock cost is to densify agricultural products in order to reduce shipping costs. To ensure a reliable feedstock supply, a collection facility could diversify their providers or feedstock types and specs, and or expand their supply radius. In the case of uncertainty, due to the weather events, precision agriculture devices such as advanced in-field aerial or satellite sensors could improve agricultural management practices. We all know that agricultural lands are mainly far from the big cities where population is concentrated. In this graph, red represents population and blue represents biomass per state. In the left, you can see we have California with very high population, but low biomass availability in the state. And on the opposite end of the graph, Iowa represents the flipped story to that. This geographical barrier, in addition to the temporal availability of biomass products versus the long-term energy needs, add to the challenges of resource or feedstock mobilization for the conversion of agricultural products to bioenergy, bioproducts, or biofuels. With that said, my research focuses on analyzing the economics of transporting biomaterial, particularly agricultural residues and energy crops, for biofuels, bioproducts, and biopower. And with this research, my team and I were able to tackle national challenges like the mitigation of carbon emissions, analyzing best practices for land use, and strategizing food and energy production for a growing population. Now, how much can biomass truly displace? As a colleague of mine keeps saying, you cannot assess what you cannot measure. So a lot of my research revolves around quantifying accessible biomass. The BT16 is a report by DOE. It provides us with a great estimation for how much biomass we can potentially have in the US to advance our bioeconomy. It also gives us a good understanding of where could these resources be throughout the contiguous US and different supply curves based on willingness to pay for each biomass ton. So let us look into some of these estimations in this graph. I'm just displaying the bigger feedstock players according to the BT16. Corn stover, a residue from a major cash crop, switchgrass and miscanthus, which are perennial energy crops, poplar and willow as part of the short rotation woody crops, and forest residues and trees. Oh, yeah. Today, I'll talk about how much of the available biomass is truly economically accessible. How much could we expect to pay for this feedstock for liquid energy production, and how could we mobilize these resources for conversion? Given the costs associated with the inherent characteristics of biomass, bulky, non-flowable, and aerobically unstable, a strategy that Idaho National Lab and my team has long studied is the possibility of having a collection depot close to fields that preprocesses feedstock to a format that is economically suitable and sustainable for delivery to conversion facilities or biorefineries. Hence, the value-added chain for mobilizing biomass would include preprocessing depots. Biogenic resources would be delivered from fields to depots in the form of bales, chopped biomass, or logs. At the depot, biomass will be of various nameplate capacities depending on their location and the resources nearby. And at the depots, biomass will be pre-processed, for example, into pellets to improve its storability, mobility, and density. This preprocessing allows for high-capacity transport alternatives such as rail, barge, to deliver biomass from depots to a biorefinery. It's important to note that rail and barge are cheaper transportation modes when delivering high volumes for long distances. Note that one truck holds 25 tons while one unit train can hold about 500 times that. My colleagues and I recently analyzed and published our findings on how much of corn stover and switchgrass could we mobilize according to specific quality and cost expectations. Our optimization model had an objective to maximize resource mobilization while meeting quality specs and an average cost of biomass delivered to the reactor throat. We analyzed different scenarios with different supply curves for different years and cost targets. This was a joint research project between Oak Ridge National Lab, Idaho National Lab, and researchers at North Carolina State University. We found that we could in fact deliver up to 168 million dry tons to a biorefinery throw at an average of $79 per dry ton. Now, I should also say, please, I welcome any questions that you have throughout the presentation. If you do have one, please don't feel bad of stopping me. I'm happy to answer them. So this 168 million dry tons are about 176 million oil barrels, or to go back to the initial slide, one quad. We're also looking at similar study with woody biomass. Now, the one quad that I just talked about is for herbaceous biomass. In particular, we used corn stover and switchgrass. But there's other forms of biomass that we could also throw it into the biomass pile for energy sources. So we're looking at woody biomass as a feedstock to the biorefineries. This feedstock includes forest trees, forest residues, and short rotation woody crops. This publication should be out soon, and is in this one, we estimate that these resources could display about 1 quad as well of energy consumption. Our next goal is to expand this analysis to identify costs associated with merging two renewable energy systems, where nuclear power would provide the heat and hydrogen to convert biomass for biofuel. We have a recent publication on the concept of an integrated system that combines biomass with nuclear energy. And our next step is to perform the techno-economic analysis on such system. All the papers that I talk about as well, they're on the bottom, if you can see the citation on the bottom. Another way that I also have looked at the costs associated with collecting and delivering biomass is to set up a simulation of the biomass supply chain. This way, one could change different parameters in the model to estimate the impacts of changes to the overall cost. This work is part of a simulation model that integrates weather conditions to the biomass supplied to one biorefinery. The paper for this is also under in the process. My team is also getting hands-on research to better understand the feasibility of making pellets out of miscanthus for bioenergy production. Miscanthus in particular is a perennial energy crop that can be grown on marginal lands. So is switchgrass. These marginal lands are usually not used for food crops, hence we're not competing with food or feed. Now, I want to get back to this one slide, which summarizes what my lab works on. So far, most of the projects that I've been talking about revolve around tackling the challenges to reduce feedstock cost and ensure a reliable supply, or identify locations that ensure a reliable supply to the biorefineries. But as you guys know, extreme weather conditions are ever increasing, making yield estimates harder and harder to predict. Because of where we are, North Carolina, the biggest producers of sweet potato in the US, a lot of my efforts in precision agriculture focus on this crop, sweet potatoes. I'm one of the leads of a big project funded by the PSI, the Plant Science Initiative at NC State, that we call Sweet Apps. Sweet potato, sweetpotatoanalytics.com, that's our website. And you can, if you would like to find out more about this project, it's a big project that includes Dr. Nelson as well. And in this project, we're really aiming to understand the different factors that affect sweet potato shape and size. The goal is to use machine learning algorithms to help us understand the variability in sweet potato shape and size. My major role in this project is to lead the training and workforce development of professionals that are well-versed in data science and agriculture, but also I'm leading the precision agriculture team efforts in-field technology to better understand yields. These efforts truly not only advance the production from rural communities, but also advance the knowledge to get a better grasp at handling uncertainty in agriculture with data analytics. And perhaps I'm super fast at talking, or regardless. Anyways, this is almost my last slide. I am also, as Dr. Nelson said, I'm also the creator and developer of the Agricultural Data Science Certificate that we now have fully approved at NC State, and any graduate student is able to take the classes from it towards getting the certificate. There's in total 4 classes of 3 credits or 12 credits. There's 2 classes that are fundamental to the certificate. The first one really gives you a a good background on the different statistical skills that you gotta have to be able to do data analytics. And then the second one, it's more on the advanced analytics, where we empower you with visualization techniques and the development of dashboards, and also as a bird's eye introduction of machine learning and other different data science techniques. So, and that's the one that I teach, the BAE 542. Right now it's still a BAE 590. If you are interested, please email me at any time. I'll be happy to hear from you. And then after that, it depends on, in that certificate, after that, depending on your background, if you have a background in agriculture, or from the College of Applied Science or CNR, the College of Natural Resources, then we can give you the tools to get better skills in data science. That includes classes in computer science or BAE classes by Dr. Nelson as well. And then on the other track, track A, really, if you have the opposite, or not the opposite, but a different background, if your background is computer science, mathematics, statistics, then we can, then the two electives go towards getting a better understanding of agricultural systems and biological systems, so that we can, the goal of the certificate is truly to create a workforce that it's truly versed in both agricultural systems and data science skills. And with that, I guess I am a fast speaker, or maybe I didn't time this right, but that is, oh no, I do have one more slide where about my team. There's nothing that any professor can do at a lab without their team, and I'm forever appreciative of the students that work with me. I have an excellent set of students that have been working with me, pursuing bachelor's, master's, or doctorate degrees in science and engineering. And with that, thank you for your attention, and I hope that you enjoy the rest of your day, and I'm happy to answer any questions, and I'm always available via email as well. And that's all, John. That's all I got for today. Hoping for a great discussion. Thank you guys for the class. Thank you.
Okay, everyone, it's open for questions. Please feel free to unmute yourself or enter a question into the chat if you feel like that. Okay, we have a question from Tom. What are some of the ecological costs of moving to widespread biomass production? For example, for switchgrass, would it require the conversion of existing habitat to biomass production, or the conversion of farmland?
Good question, Tom. So the reason why switchgrass and miscanthus, both of them being perennial grasses, energy crops as well, the reason why they're so attractive is because they're the characteristics that they have. We're able to grow them on marginal lands, or lands that are not currently crop lands. In terms of the ecological cost of converting or those marginal lands to switchgrass or miscanthus, that's a really good point. I would love to collaborate if you have ideas on how to evaluate those costs, because absolutely, that should be absolutely part of our analysis as well. There you go.
Thanks. I guess to maybe to follow up, I guess the idea is that those products would be like grown on habitat that's converted to energy production, or would they be grown on like farmland that's no longer viable? I guess what I'm trying to figure out, I guess, is if a bunch of habitat is being created to or a bunch of habitats being converted over to biomass production to agriculture, then that, I guess, would strike me as some sort of ecological cost.
No, I agree. You're right. You're right. We're definitely, I mean, every time we are trying to change what's out there, that definitely it's an increase. There's a cost associated with the ecological change. I personally have never really adventured that way. You're right. It's absolutely a cost that needs to be, as well as that needs to be addressed, as well as, you know, the cost of the opportunity cost of not having or continuing to be dependent from petroleum that is outsourced, and all the different social costs that we do incur. You're right. And because of that too, I think USDA, DOE, NSF, they're also pushing more and more to have more social scientists and ecological scientists so that we better address those questions. You're right, Tom. I agree.
Thanks.
I see Francois. How important is North Carolina biomass and NC State is in the overall picture of your research? NC State as the state of North Carolina or the university, Francois? University, gotcha. So how important is North Carolina biomass? We are a very diverse state in terms of climate. Because of that, we have the potential to truly, hopefully better represent various different climates, for example, for research, for analyzing different yields and different climates. So because of that, we're truly well positioned for biomass analysis. In terms of the university, we also truly have, you know, with the Plant Science Initiative and the Data Science Academy, for example, we continue to have a better push for creating this workforce that is well versed in data analytics, but also the agricultural systems and the biological systems. So in terms of creating biomass or for biofuels in the state of North Carolina, absolutely. We also, so when I think of biomass, it's not only crops, it's also wood. So for example, wood residues or short rotation woody crops. And we are, if not the first, a biggest producer of wood pellets, right? So that is also another avenue that we can perhaps leverage to make in-house production of biofuels. It just depends on, you know, and now I work on sweet potato a lot, and we do have, you know, we're the top state producers of sweet potatoes, and there's a lot of waste in there too, and it's biogenic and it's flowable, and we already know how to store it, you know, for the whole year. So there is potential of biomass there as well. I know that some professors in the past have explored those avenues, and I would like to reignite that with the decrease in oil prices. A lot of the bioenergy studies sort of got neglected a little bit, but now that, you know, we're more and more becoming more aware of this extreme weather conditions, I think there's a new push again to try to mitigate climate change as well. Oh, it's not. Miscanthus is non-native and switchgrass is native. I think I've seen it on an invasive list somewhere. Do producers give preference to one or the other? We grow miscanthus here. You're right, it's non-native, but there is a lot of research done to different varieties. Right now in the state of North Carolina, we do produce miscanthus for to serve as bedding for chickens. If somebody else knows, has a different opinion, please let me know, because this is what I know. You're right, miscanthus is not native, but we are working with a lot of different varieties that might be able to be to surpass, the potential when you compare miscanthus versus switchgrass. Another thing to point out is based on the econometric analysis done at Oak Ridge National Lab, we see that, or their analysis show that over time, miscanthus produces a lot more than switchgrass. They, if you looked at the billion-ton study results, at the beginning, it's an analysis for various years, for supply curves for various years. And at the beginning, yes, switchgrass nationwide beats miscanthus, but towards the end, the miscanthus starts becoming more adopted throughout the whole nation. So in my opinion, there's still debate of which one, miscanthus or switchgrass, would be better. I think it also depends on where you are geographically in the whole United States as well. But they're both really good energy grasses that we could explore, again, to not compete with food and feed is the goal. Oh, there's another question. Nice. Is there a preference between woody species like poplar and the different grass species? Thank you, John. Probably my student that's here, Tasman, can better remember this. So in the analysis that we're currently doing, we're looking at the quality specs, or the quality that is required at the biorefinery. And in terms of woody biomass, the big quality component is, or characteristic, is ash content. So it depends on the ash content on the different wood varieties. If I remember correctly, poplar had the lowest ash, hence it always supersedes everybody else, but I could be wrong. Oh, Tasman.
Yeah. Thank you, Dr. Jones. So yeah, about ash. So depending on the ash content, so poplar was kind of in the middle. So willow had the highest, and poplar was right before willow. So yeah, it was picked mostly because if we want to blend, for example, if we want to achieve 1.5% ash, that what we're targeting, we want a blend of poplar and trees and residues, because trees and residues had the lowest ash content among all the woody residues. Yeah, so that's why poplar was picked from the short rotation woody crops. It was always the top one to contribute between the short rotation woody crops: pine, poplar, willow, and eucalyptus. That's the four that we were talking about.
So pine was on top?
Yeah, so pine had the lowest ash content. Yeah,
gotcha.
It had 0.8%, and poplar had somewhere around 1.7% ash content, like after we harvest it, like from the ground. Yeah, at that point.
Yeah, so in our mathematical models, we try to capture as much we can all those different characteristics, which truly, yes, we should also think about how can we incorporate the ecological aspects, the ecological cost. But in terms of trying the preferences between the different woody species, the model will pick the one with smallest ash, but also so the model also has to meet a certain cost, make sure to meet some capacity constraints and so on. So John, I can't give you a straight up answer on which one is more preferred, but the lowest ash content, the easier it is at the biorefinery. Thank you, John. I see my colleague Gary Robertson join as well. Thanks for coming. We're now in the questions section.
Daniela, I have a question. Regarding the marginalized landscapes, does your group do any mapping or modeling of where these landscapes are found? Can you expound, if they do, can you expound on that?
Yes, so currently nobody in the lab, not currently, nobody in the lab really does a lot of remote sensing except for a visiting scholar that has come recently. His name is Fernando. So what I have done in the past is utilize like the national land cover data to identify where exactly all these marginal lands are. For example, when I'm trying to identify where this biomass would be, and we truly have most of our data is on a county level, and instead of assuming that all of the biomass will be equally distributed throughout the county, we often say already knowing where the marginal lands is within that county, this is where we believe the biomass is, so that we have a more precise estimation of the location of this biomass, and that is truly to better understand the cost estimates of transporting that biomass to another county, or if there's enough biomass in that area to truly create a preprocessing facility or a bio conversion facility.
Thank you.
Yeah, I have a I didn't talk about it today. I have a paper as well where we did use a lot of GIS analysis using the national land the national land cover data set to figure out just that as well, to see if we only look at it spatially, where are these clusters of biomass for conversion.
Anyone have any more questions? Please just feel free to unmute or type it in the chat.
I'm also always looking to find new ways to collaborate with, especially people at the Center of Geospatial Analytics, because I mean, I truly, it's a truly diverse set of researchers at the center, and I'm happy to collaborate. Please reach out if any of this sparks any interest to you, or if it makes sense for us to collaborate.
Okay, if there are no further questions, we'll wrap it up. And I want to thank everyone for the questions you submitted. Thank you, Natalie, for the introduction, and of course, thank you, Daniela, for the presentation. Really enjoyed it.
Thank you, John. Thank you, guys.
And there is a post-forum social as usual, and it starts at 5:15, I believe, at Transfer Company Food Hall, 500 East Davie Street, Raleigh. If anyone is interested in attending, please do so.
All right, thank you so much, guys.
Thank you.